Good evening, everyone. My name is Seda Said, and this is our eighth interactive session. And today we will be doing some questions on consolidation. Last interactive session, we studied shear strength, shear stress, and we did some questions related to it. This week, we are going to do some questions on consolidation. So that is what was covered in week 8. Okay, so let's get to it. Okay, so this is the first question. Following are the results of a laboratory consolidation test on a soil specimen obtained from the field. So the dry mass of specimen is 128 grams. Height of specimen at the beginning of the test is I'll show you how. First, let's discuss the consolidation test a bit. So in a consolidation test, we use an oedometer. It has something like this. Okay, so it has a smaller depth than the length. Like in triaxial, we have a sample that is longer, and then we put load here and we see some kind of a shear failure. But in oedometer test, what we want is we want uniaxial loading. These two faces are confined because we don't want any uh, lateral movement. We want displacement only in this direction. So it's a ring type of thing. If you remember, in triaxial test, we have a membrane surrounding the sample, but the membrane is flexible such that when we load this, it can bulge outwards. So lateral displacement of soil takes place in a triaxial test. Even though there is confining pressure here, but this boundary is free to move. So we can see bulging here. Same is the case with UCS also. In UCS also, we so let me actually show you. In UCS, unconfined compression test, we have a cylindrical sample and then there is no confinement here. It is just like a test to do on a steel bar. So this will be the upper part, this will be the lower part, and you just place a sample here and you apply load here. So this is done on cohesive soils. If we talk about UCS, this is done on cohesive soils. Why? Because you can't have this kind of a sample for a cohesionless soil. It has to have cohesion for it to be able to form this kind of a sample. If you have a cohesionless soil like a sand, it will just be a pile. Then same kind of sample, same material. There is this instrument through which we make this sample. Uh, we make this sample. Oh, in triaxial test, there is an outer cell, and there is this platform, and in the outer cell we fill water. What this water does is that it provides uniform pressure on all sides of this cylindrical sample. Okay, so but this sample is enclosed in a membrane, a rubber membrane usually, due to which it is free to move. So these two ends are fixed and these are movable. And in consolidation test, we have a sample that has a smaller height. It is still cylindrical. This is enclosed in a steel ring kind of structure, and we apply pressure such that only displacement that can take place is in the vertical direction and there is no displacement in the horizontal direction. That is what we do in the consolidation test. So let's get back to the consolidation test. And in consolidation test, we have very gradual loading such that the as more and more load is applied, more water is allowed to dissipate for the consolidation to take place. So we have been given the height of the specimen at the beginning of the test is 2.4 centimeter. At the beginning is 2.4 centimeter. And the area of the specimen is 30.68 centimeter square. So how much is the diameter then? Let's calculate first so that you understand that it has a larger diameter than the height. One second, let me get my calculator. Okay, 30 centimeter, 30.68 divided by pi. Square root. That is 3.1 centimeter radius. So the diameter is 6.25 centimeter. Okay. So the dry mass of the specimen is given, height of the specimen is given, area is given, GS is given. Make the necessary calculations and draw the E versus sigma dash curve, and we have been given the effective pressure at each loading step. Like we have increased the pressure 0.5. These are the pressure readings, and we have the settlement here, final height of specimen, or uh, we can subtract. Let's actually open an Excel sheet and try to plot this. What we need to do is make E versus sigma dash. Okay, let's open up an Excel sheet. And let us call it interactive session 8. Okay, so the effective stress let's call this sigma dash is 0, 0.5, 1, 2, 4, 8, 16, and 32. Oh, 1, 2, 4, 8, 16, and 32. And we have final height in centimeter, 2.54, 2.488, 2.465, 2.431, 2.389, 2.324, 2.225, 2.115. Let me check again. 2.54, 2.488, 2.465, 2.431, 2.389, 2.324, 2.225, and 2.115. Okay, that seems correct. So, excuse me. Uh, let's calculate the height of solids from this. Let me actually open this in a smaller space. So, how do we calculate the height of solids from here? See, if we have a specimen of height h and we consolidate it and we have a final height, say we have a final HF, and this is the change in height. So you know that GS is equivalent to gamma S over gamma W, and gamma S is equivalent to GS gamma W, and we know that gamma S is weight of solids over volume of solids. This is equivalent to GS gamma W. So the volume of solids is equivalent to weight of solids over GS gamma W, isn't it? And we know volume is area into height. So height of solids into area of solids is equivalent to weight over GS gamma W. Let's assume that this is the area of the area of solids is equal to the area of specimen, then we will have height of solids is equivalent to weight of solids over area into GS gamma W. So from this we know WS is 128 gram. Area has been given as 30.68. G has been given as 2.75, and let's take this as 1 gram per cc. So height of solids we can calculate at initial and where's this? Okay, let's calculate then based on the formula given, the formula that we just saw. So from this we calculate the height of solids, initial height of solids, and final height of solids. So if this is the height of solid, let me actually reframe here. If we assume that the area of solids is equal to the area of the specimen, this was not after loading, I was here we will have some voids. Let us assume that all the voids have been taken and they have been adjusted in the upper part where we have this two-phase diagram. Let this be solids, let these be voids. Okay, so just now as I showed that GS is equivalent to gamma S over gamma W, that implies gamma S is equivalent to GS gamma W, that is weight of solids over volume of solids is equivalent to GS gamma W, and volume of solids is equivalent to weight of solids over GS gamma W, that implies area of solids into height of solids is equivalent to GWS over GS gamma W. Height of solids here will be weight of solids over area GS gamma W. So this will be the height of solids and this will be the height of voids. So we will calculate for each reading, we will calculate, we already know the height of solids. Height of solids is not going to change. Only thing that is going to change is the height of voids as we go on with the compression. So first let's calculate the height of solids and then let's calculate HV for each time step. And from HV we can calculate the void ratio, as we know E naught is equivalent to volume of voids over volume of solids. This will be area into height of voids over area into height of solids. Okay, this will be constant and this will change for each loading. Let's calculate that. First, let's calculate height of solids. Let me input the data first. Okay. So we have GS is 2.75. Then we have H naught is 2.54. Then we have area is 30.68 and W naught. W naught is 128 grams. Okay. So H of S, I mean to say height of solids will be W naught divided by G of S into area and gamma W is 1 gram per cc. Technically, this has to be multiplied with gamma W. So we have a height of solids of 1.5 centimeter. So initially, let's calculate height of voids here. Height of voids is height mi minus height of solids. So this will be this minus, so this is how the height is changing, and as we discussed, the void ratio will be h height of voids over height of solids. This will be this over this. Let's lock it. I hope it is clear to everybody how we got the height of solids. I will go over it once again. So in the specimen, initial specimen, or in the actual specimen, there are voids as well as there are solids. So when we talk about height of solids, we are actually talking about the two-phase diagram, in which we say that the soil has actually three phases. But in consolidation, what we do is we saturate the sample, and we are assuming here all these voids are filled with water. Um, and we're talking about two phases only, that is voids. Even if it is not saturated, still the sample will have solids and voids, and we want to calculate what part of this two-phase sample, what will be the height of these solids, and we calculate it from here, height of solid, and from the total height we can know the height of voids. Why we are talking about height is because the sample is cylindrical, it's symmetric, so the area of both sections is same. So we can cancel that, and we can uh, calculate the void ratio to height itself. So then we take void ratio is equivalent to volume of voids over volume of solids, which will be height of voids over height of solids. And now we have been given height at each increment, stress increment, and we subtract height of solids from these, all of these, because when we consolidate, what we are doing is we are squeezing out the water from the pores. We are decreasing the pores of the soil, but we are not touching the solids. Okay, we are not changing the state of the solids. And now we have our sigma as well as E. Now let us plot it. The sigma will be on a log scale. In the actually, let me just plot it. Uh, I should have added a scatter plot because so we can call this E versus log sigma. X will be sigma, Y will be E, so the X axis will be log scale. Okay, so actually let me do one thing. One maximum is 100. Okay, and then we have minor, let us have at 3. 3. Okay, let me add axis titles. This will be log effective stress. This is in ton per feet square, and here we will have void ratio E. Now we can add a trend line. Okay, let's take it from 0.2 to 0.8. And let's take this from 0.1 to 100. Okay, so this will be our curve, E versus log sigma. That is what was asked. Is there something else? This is the variation. Okay. Make necessary calculations and draw an E versus log of sigma. Okay, I think we have done that. Let's do one more thing. Let's copy this here. Okay, that's fine. Okay, so let's move on to the next question. The next question says that it gives us the results of a consolidation test, and what we need to do is, what are we supposed to do in this question? Let me check. Okay, we are supposed to calculate the compression index and the ratio CS over CC. You know, CS is the slope of reloading line swelling index, and CC is the compressible, excuse me, compression index. And on the basis of the average E log sigma plot, calculate the void ratio at sigma naught equals 1000 kilonewton per meter square. Let me, this is sigma dash and sigma naught dash. Okay, so we have been given the void ratio and we have been given the pressure, and as you can see here, the loading is increasing, and after this we are going towards the unloading. So what we will do is we will plot the log E versus log sigma plot for loading as well as unloading, and from the loading line we can get the CC, which is the slope of that curve, and from the unloading line we will get the CS, which is the slope of the unloading curve, and on that basis we will calculate the void ratio at sigma naught equals 1000 kilonewton per meter square. Let us do that. So this was question 1. Let's take question 2. Did I copy this? No, I did not. Okay. Okay. So let's plot. And this is again E versus log of effective stress. X value will be the pressure, Y value will be the void ratio. Okay. And this will be in log scale. And okay. Actually, what I should have done is I should have taken two plots. So I will take this as one plot, and then I will add this, we will call loading, and then we will add unloading from here. Okay. Okay. And now we can do what we can do. We can have trend lines. Something like this for loading and linear for unloading. Okay. So we will have mm, for loading, we will predict backward or do we predict forward? 2 periods. Okay. Uh, Actually, the thing is that we have a pre-consolidation stress somewhere here, and we will have a trend line from here. This is at 200. Okay, so this will be the pre-consolidation stress. So let's do one thing. Up till here, let's take one. Up till 200, let's take normally consolidated loading. This is normally consolidated loading. No, this is over consolidated loading. Sorry. Okay. Then we add normally consolidated loading. Okay. From x is equivalent to this and y is equivalent to this. Okay. So if now I add a trend line to it, it will be a better picture. Excuse me. So I will forecast forward one period, backward one period. Linear. Uh, it has to be logarithmic because this graph is logarithmic. And this also has to be logarithmic. Okay. And backward 5 periods, forward 5 periods. But it's not forecasting. I don't know why. Why isn't it forecasting? Trend line options. What about one period? I don't know why it's not forecasting, but I think you get the idea that I'm trying to say. What we will do is we will just simply insert a line and try to align it with it, because I don't want to spend more time on trying to get it to forecast. Okay, okay. So this is our the slope of our CC, and this will be the slope of our unloading line. So what the question is asking, so from this branch, if we take these three for CC and these three we can take for CS, we will get CC is the slope of this. It will be E1, E2 minus E1, 0. What was the question again? Okay, CC by CS. Okay, so the CC we can have 0.69 minus, how much is this? 0.52 divided by, this will be log to the base 10 of, why am I writing it like this? Log to the base 10 of this 400, log to the base 10 of 800 minus 400. 1600 minus has to be 1600 over 400. And here it is this minus this. So we will have a value of 0.28. And for CS, we can take these 3 points. We will have 0.57 minus 0.535 over log 10 of 800 over 200. So it will be about 0.05. So this is approximate almost 0.06 and 0.28, and the ratio Cc over Cs will be Cs over Cc actually. This is about, was it Cs over Cc or Cc over Cs? Cs over Cc. This is about 0.2. Cs over Cc is 0.2. So let us translate it back to our slide with the diagram. Copy this. I just paste it here. I did not write the jar titles. Actually, I did write the jar titles. What happened to them? Okay, I did not write the jar titles. So this was log of effective stress. This was void ratio. E versus log sigma. So these are the points that we identified, and from our calculations we got, let me note the results here so it's easy for you in the PPT. E C equals 0.28, Cs equals 0.06, Cs over Cc equals 0.206. Okay, okay. So this was for question number 2. Now let's look at the, okay, I forgot this part. On the basis of this average E log sigma plot, calculate the void ratio at sigma naught equals 1000. So, excuse me. So we know the Cc, okay. Let's take sigma naught at 1000. We need to calculate this thing here, this thing. Void ratio at sigma naught is equal to, which means that we have loaded here and at 1000 we will unload. Do you understand what sigma naught means? Sigma naught means that there is a pre-consolidation. I'll show you. So here, if you see, there is a pre-consolidation pressure. As you know that soil has a memory. For example, this is a freshly formed or freshly placed soil, and I put place a weight over it. When you place soil very loosely, as you step over it, it will compress a lot. But sometimes, like in cricket pitches or other like tamped grounds, the soil is very stiff. It will not crumple, or it will not compress with you stomping your feet on it. So what happens is that this soil, if I place a load of 100 kilonewton on it, and the soil before this soil before in its lifetime has only been subjected to 50 kilonewton, what will happen is, as I am loading this till 50 kilonewton, it will resist, as in this. And if 50 kilonewton is the pre-consolidation pressure is the maximum pressure that it had endured, that I had. For example, let's not talk about the history. Let's say that I have a soil and I have a load of 100 kilonewton on it. And I know for a fact that this soil will be will act as over consolidated soil when I put on a load less than 100 kilonewton, because right now there is a 100 kilonewton load on it, isn't it? Now, I don't know the history of the soil. Maybe initially it was loaded up to 200 kilonewton. But for argument's sake, let us say that this is the pre-consolidation pressure. Yeah, this is the maximum load that the soil has been subjected to. So what will happen, that up till that stress, pre-consolidation pressure, the soil will resist change to its volume. As you see, as the load is increasing, the volume is not increasing that much. But as soon as you cross this stage of pre-consolidation pressure, it will start to increasingly deform. It will show high volumetric strain, because now you are in the zone where you are causing um, uh, um, the soil to undergo plastic deformation, because now as soon as you unload it, it will not go back to its original shape. It will go back somewhere here. Now it is permanently deformed to some extent. Okay, so as I was saying, that initially, if you would see from here, we could see that the pre-consolidation pressure was somewhat about 100 kilonewton. Pre-consolidation pressure. After 100 kilonewton, it started increasingly showing volumetric deformation. Now it is saying that on the basis of average E sigma log, calculate the void ratio at sigma naught equals 1000, which means that when it reaches here, we will stop the loading and we will unload it. Or like this is not taking place. So what will happen is this soil will first it will see now what the soil will do. Initially, this was the pre-consolidation pressure right here. So it went from this to this loading. Now we have stopped the loading here, and if we unload it, unloading will follow this line. The second line, it will follow like this. Excuse me. Okay, this is the path that it will follow. So because we know the slope of this line, this is CS, we know the initial final like C naught is 1000, and at sigma equals 0, let us say, we will get um, the void ratio as this will be void ratio when it is on NC line 1000, and then it will unload void ratio when it is on reloading line. So E loading, we already know somewhere here, will be about, for argument's sake, let us say it is 0.6. Okay, and when it is on unloading line, it will be CS is the slope. Slope is E by V. E is here, it is about 0, almost 0.8 minus 0.6 over 1000. This part, this is 0.8, 0.6, this is 1000, this will be we know that the 0.8, 0.6, 1000. Okay, let me add another slide to it. Let's rub this off. So we know that Cc equals E1 minus E2 over log of sigma 2 over sigma 1. If this is 1000, reconsolidation pressure on the loading line. Okay, on the loading line, we are taking E1 as 0.61, sigma 1 as 1600, mm, actually let me take 400 and 800, 0.69, and 400 is, sigma 1 is 400, and let's take E2 as question mark and sigma 2 as 1000. Okay, we want to calculate it here on this line. So we know cc is 0.23. So 0.23 equals 0.69 minus void ratio that we want over log of 1000 over 400. So let's calculate. See, this is on the loading and loading line. 0.69 minus, no, 0.23 into log the base 10, 1000 over 400. So we will have E about 0.59 at sigma is equivalent to 1000 on the loading line. But if we unload it P naught, if we unload it, because it is talking about sigma naught dash, that is why I thought that it's talking about reconsolidation pressure, but it's only talking about sigma here. If it was talking about unloading, we would have to take from here a line to the back with this. Let's calculate where this, when unloaded, what will be the void ratio. The void ratio will be on unloading, so we have E1 is 0.59, E2 we want to calculate, sigma 1 is 1000 and sigma 2 is 0. Let's call sigma 2 1. Okay, let's calculate at 1, not at 0, because then we'll have issue with the logarithmic scale. So we have 0.05 equals E2 minus 0.59 over log the base 10, 1000 over 1. Okay, so this will be 0.05 into log of 1000 plus 0.59. So the E2 will be 0.74. So it will come out to be somewhere here. So the unloading will take place like this. Okay, and the soil void ratio after unloading will be 0.74. Okay, so let's move on to the next question. We can take a short break, but okay, let's do it after. So the next question. A soil profile a soil profile is shown below. If a uniformly distributed load sigma delta sigma is applied at the ground surface, what is the settlement of the clay layer caused by primary consolidation? Okay, now we are talking about primary and secondary consolidation. As you have studied primary consolidation, excuse me, excuse me. Primary consolidation is due to change in void ratio, as we discussed earlier. Like if this is a soil sample and this is its phase diagram, it will have some solids and it will have some voids. And with consolidation, what happens is the void space is reduced while the solid space remains same. And completely consolidated, it will have minimum number of voids. It cannot be zero. You cannot have zero voids, because then it will cease to exist as a porous material and it will become a solid like a steel. And that is not how soil is. Soil is a porous material. So it will have a minimum voids. So that configuration is reached with primary consolidation, which takes place primary consolidation which takes place due to expulsion of pore water from voids, or a reduction in void ratio. See, up till now, what we were saying is that what will happen is that only and only voids are changing, solids and heights of solids will remain same. Now, this scenario will change in secondary consolidation. Secondary consolidation takes place when your soil structure starts to change. There are changes in soil structure due to long term loading or strain. It's just like uh, you see, you all have that rubber bands, or this rubber bands that you put in your hair, that are very elastic. So after some time, after use and use and use and use, what will happen that they will lose their shape. They will become mm, deformed. So this deformation is called creep. It's called creep, and it happens due to inherent change in the structure of the soil and not due to the expulsion of or reduction of voids. So initially what will happen, all the voids will change, and then secondary consolidation will take place, in which our structure of the system is changing. And in soils it is not that significant, I must say, because it does not result into that much of uh, settlement, and also it is a very long term process. However, there are some certain kind of soils where there very it is a very prominent thing, like soft soils. You will see creep will take place at a sustained loading or a sustained state of strain. Okay. uh, So now we will do a question on primary consolidation. We are talking only about the change in void ratio right now, not the change in structure of the solids. Okay. A soil profile is shown if a uniformly distributed load, delta sigma, is applied at the ground surface. What is the settlement of the clay layer caused by primary consolidation? If the clay is normally okay, initially they're talking about a normally consolidated clay. One second. Okay, initially the clay is normally consolidated, which means that whatever loading that you are putting here is the maximum loading that the soil has reached to in its history, which means that when we were talking about here, it was this part of the loading, isn't it? That it will not show that much resistance because it has not been loaded so much in the past. So it will show high settlement. High settlement. This is normally consolidated. Second, the pre-consolidation pressure is 200 kilonewton per meter square. Now you see. Now what is now first of all let's see how much overburden this soil will have. Okay. So let's calculate the average effective stress at the middle of the layer. So this will be, let's calculate it from here. Okay, we will have, to try to draw a better diagram. Okay, and then we will have, this will be 100 kilonewton per meter square, isn't it? This will be the stress due to the load, and then we will have effective stress due to this gamma dry is 14. This will be 2 into 14. Remember, we are talking about effective stress. I'm trying so hard kindly. Okay, and then we will have up till here gamma saturated is 18, so we will have, let us take gamma W as 10, and we will have gamma submerged as 8 kilonewton per meter cube. So we will have 4 into 8. Here we have 19, so we will have 9 kilometer per meter cube. This will be 3.5 over 2, which will be 1.5, 1.75. 1 point, this will be 1.75 into 9. So what will be the total effective stress? Sigma naught at center of layer will be 2 into 14, 100 plus 2 into 14 plus 4 into 8 plus 1.75 into 9. This will be, let's calculate, 175.75. Now you see, what is the pre-consolidation pressure? The pre-consolidation pressure here is 175.75. So that means, how can this be? So in this case, it means that since the soil is normally consolidated, it means that pre-consolidation pressure here is the pressure, overburden pressure, which is 175.75 kilonewton per meter square. Actually, it is 75 without the delta sigma. No? So it is 75.75 kilonewton per meter square, and delta sigma we are taking, we are increasing the load up to 100 kilonewton per meter square. So what will happen is up till 75.75 kilonewton square, it will behave like this. And as soon as pre-consolidation pressure will reach, it will increase the volumetric deformation. Now the case 2 is that the pre-consolidation pressure is 200 kilonewton per meter square. Okay, so in case 2, what will happen is that if we apply 100 kilonewton per meter square loading here, actually let me show you through the question itself. It will be clearer. This way it may become a little confusing. So sigma naught we have calculated. Let me give you the value of Cc, and then Cs will be 1 by 5 over Cc will be 0.17805, 0.036. Okay, so we know the primary consolidation is equivalent to Cc over 1 plus E times H log of sigma naught dash plus delta sigma dash over sigma naught dash. You see here sigma naught dash is 75, sigma naught dash is less than delta sigma. Delta sigma is 100 kilonewton per meter square. So this will be 0.178 over 1 plus E is 0.8, 0.8 into H is 3.5, 3.5, and this is sand, which means that it has double drainage. This will be H by 2. Oh, this is fine. 75.75 plus 100 over 75.75. So what I was saying was that in this scenario, we will take the value of Cc. Why? Because this is normally consolidated, because delta sigma is greater than sigma naught. This comes out to be 126 mm. Now for the second case, the pre-consolidation pressure sigma naught is 200 kilonewton per meter square. Okay, and delta sigma is 100 kilonewton per meter square. Okay, so what will happen is that maximum load that will be reached here is initially it is 75.5 kilonewton, isn't it? So when you apply this loading, the total load here will become 175.5 kilonewton per meter cube, meter square. So which is less than the sigma naught, which means that the whole range of loading from 75 to 175 is in over consolidated state. So we simply use CS here. So we will use settlement will be primary settlement will be Cs over 1 plus E H log of sigma naught, not sigma naught, but uh, yes, like 75.75 plus 100 over 75.75. Okay, so is this will just be 1 by 5 of 126. It will be about 25 mm. But now look at the third and interesting case. See, the pre-consolidation pressure is 150 kilonewton. In third case, pre-consolidation pressure is 150 kilonewton. But the maximum pressure that the soil will reach is 175. So what will happen is initially it was at 75.75 kilonewton per meter square loading. Now we are gradually increasing the loading. It will increase. Where does it have to go? It has to go maximum up to 175.75 kilonewton. But as soon as it reaches 150, you see 150 was the pre-consolidation pressure. This part will behave as over-consolidated and this part will behave as normally consolidated. So if we go back here, if 150 is here, the soil loading will start at about 75. It will behave as OC soil with CS slope, and as soon as it reaches 150, it crosses over and becomes NC soil. Okay, for this we have to split the term for the calculation of settlement into two parts, the OC part and the NC part. Okay, so for the OC part, CS will be settlement will be CS over 1 plus E naught H log of initial is 75.75 and you want to reach up to 150. So it will be 150 over 75.75 plus now normally consolidated CC over 1 plus E naught H log. Now you are moving from 150 to 175. So the total will be 175 over 150. Okay. Basically what it is doing is, let's 150 minus 75.75. So the delta sigma here is 74.25 and sigma naught here is 75.75 and delta sigma here is 175.75 minus 150, 25.75 and sigma naught is 150. So in the numerator you have sigma naught plus delta sigma. This is this in this case and this is this in this case. That is what we are doing. Okay, so let us calculate. Point 0.0356 over 1.8 into 3.5 log 150 over 76.08 plus, this was actually 75.75, 0.178 into 3.5 divided by 1.8 into log of 175.75 over 150, and this will come out to be about 44.5 mm. And if you see the three values, 126, 25 and 44, we have three values, 126, 25 and 44. So the soil with 126 was NC soil, and as you can see, NC soil shows high compressibility. This soil was totally over consolidated. Throughout this, it was over consolidated throughout the stress range. And third case was that half of it was over consolidated, half of it was normally consolidated. So it is greater than the over consolidated case, but lesser than the purely normally consolidated case, and that makes sense. For each part, calculate and plot a graph of E versus the beginning and end of consolidation. Okay, so now let us draw a plot. So for drawing a plot for all of them at end of consolidation, we know E naught was same for all of the cases. Case 1, case 2, case 3, E naught was 0.8, E naught was 0.8, and E naught was 0.8. And we need to calculate the final, and we calculated the settlement. Delta was 126 mm, delta was about 25 mm, and delta was about 44 mm. Okay. C01 plus E naught H delta. So we know the E naught. This was 1.8 for all of them. 1.8 times delta is Cc H log. Let me recollect this. Okay, so you see from the uh, expression we have primary settlement is equivalent to Cc over 1 plus E H log of sigma plus delta sigma over sigma, isn't it? So if we take this is basically delta H, and if we take delta H over H, this is the strain. And basically delta H over H is equivalent to delta E over 1 plus E, and 1 plus E into delta H over H will give us change in void ratio. So we rearrange this, we get change in void ratio equals 1 plus E times delta H over H equals Cc log to the base 10 sigma plus delta sigma over sigma. Now this portion of these equations, let's take only this portion, Cs log 150 over this Cc and this, and we will get the three changes in void ratios. So instead of writing the settlements here, let me write delta E and delta E, and from this we can get final EF will be E naught minus delta E. EF is equivalent to E naught minus delta E. EF equals E naught minus delta E. So this is the first one is how much was CS? Point, no, the first one is the CC. 0.178 into log of 175.75, 75.75. This is 0.065. This is, so EF, let me write in another color. EF is 0.735. In this case, EF is 0.787, And in the third case, EF will be 0.771. So for plotting this question, let me actually first fill the data for the question. So for the loading, let this be case 1. Actually, let me write it here. Case 1, 1, 2, and 3. We have pre-consolidation pressures. This was 75.75. This was 100. No, this was 200. And then this was 150. And we have a delta sigma, which was 100 in all cases. And we had an E naught, which was 0.8 in all cases. And we had an EF, which was 0.735, 0.787, 0.771. We also had an effective stress, which was 75.75 in all cases. Okay, and also we had CCCS, but I think that is not required. Oh, okay, also we had the final stress, which was same 175.75 in each case. Okay, so what we will do is we will insert this. So the X will be case 1, X will be this and this, and Y will be E naught and EF. Okay, and we will have case 2, in which the X again will be same, but Y will be this. Actually, instead of case, let me write PC equal 75.75. PC equal 100. not 100, 200. Here we have PC equals 150 kilonewton per meter square. X is same, Y is this. Okay, and okay, this will be log scale. This will start from 10. Okay, and 550. Okay, and this, let's go from 0.7 to 0.81. Okay, let me add axis, legend, axis titles. This is log of effective stress and void ratio. Okay, okay. Hmm. So if you can see here, for normally consolidated, you have a higher decrease in volumetric void ratio. For 150 it is medium, and for over consolidated it is, so the slope here will be the CS. This is CC, while this will be something in between. Okay, let me check. Okay, so I had one more question lined for today, but it seems like our time is up. But let me just go through this question as quickly as possible. So the normally consolidated clay layer in the field, for a normally consolidated clay layer in the field, following values are given. Thickness is given, void ratio is given, compression index is given, average effective pressure on the clay is given. sigma, delta sigma, secondary compression index is given. What is the total consolidation settlement after 5 years? 5 years after completion of primary consolidation settlement. Time of completion of primary settlement is 1.5 years. Okay. So what we will do quickly is we will calculate the primary as well as the secondary consolidation of this. Okay. So the primary consolidation settlement will be, see, this is not how we will do it because we have been given the time here. Okay. Delta sigma sigma Cc E naught H. So we have been given everything. Cs is equivalent to 0.28 over 1 plus 0.8 into 8.5 into log of 2650 plus 970 over 2650. Okay, so let's calculate. This is 0.28 into 8.5 into log of 10, 2650 plus 970 divided by 2650. This will be about 180 mm. But let's calculate delta E, which will be simply 0.28 into log of 2650 plus 970 over 2650. This will come out to be 0.038. Okay, so we know that the secondary consolidation index is given like this. This is primary consolidation. This is the void ratio after primary consolidation, and EP is equivalent to E naught minus delta E primary, which will be 0.8 minus 0.038. Okay, okay, we have to multiply this by 12 to get an inch. 8.5 into 12, this is 102 inch, and here we will have 180 into 2.15 inch. I forgot the scale is in feet and inches. Okay, and in we got delta, we got primary consolidation SC is equivalent to 2.15 inch. We got EP equivalent to 0.762 from here. Okay, and we will get the secondary consolidation as C alpha, which is 0.02 over 1 plus 0.762, which is 0.011. So the secondary consolidation settlement will be C alpha dash H log T2 over T1 equivalent to 0.011 into 8.5 into 12 log time of secondary consolidation, time of primary consolidation. This will be 0.59 inches. So total consolidation will be SC plus SS, which will be 2.15 plus 0.59 equivalent to 2.74 inch. As I mentioned, secondary consolidation is quite small as compared to primary consolidation. Okay guys, that was it for today. Thank you very much.